I'm going to explain this nice result on a quick way to find residues if you have a pole. I'm going to give you two examples in the proof. So example 1 is I'm going to find the residue at z equals 0 of 5z squared plus 1 over z cubed. So almost immediately, if you just do this out, right, you might find that 5z squared plus 1 over z cubed is equal to 5 over z plus 1 over z cubed. So the residue should be 5. So we're going to see that that's true by using this method here. So this says that I've got a pole of order 3 here. So I just do 1 over 3 minus 1 factorial times, and I'm going to even tell you that you can basically ignore this limit thing. This limit thing is a technicality here. I'll discuss that when we get to the proof. And then I'm going to take the second derivative of 5z squared plus 1. Well, the first derivative is going to be 10z, and the second derivative is going to be 10. And then I'm going to plug in z equals 0 into 10, which is going to give us 10. So that gives us 1/2 times 10, which equals 5, which is what we thought it was going to be. Let me give you a second example here. A second example is I want to find the residue at z equals I of sine z over, how about z minus I to the 5th. Well, this theorem says, right, this is a pole of order 5, so I do 1 over 5 minus 1 factorial, and then I need to take the fourth derivative, 5 minus 1, take the fourth derivative of sine z. And I'm going to evaluate that at z equals I. Well, let's see. One derivative of sine gives me cosine. Two derivatives gives me negative sine. Three derivatives gives me negative cosine. Four derivatives gives me sine. Oh, so this is 1 over 4 factorial times sine of I, which equals sine of I over 24 factorial. Just 24, sorry, not 24 factorial. And that's the residue. You don't need to do the Laurent series or anything. So this just gives you a quick way of doing it. So now I'm going to move on to the proof. Alright, so I'm going to discuss the proof of this, and the proof really just uses a couple key facts. The first fact is that holomorphic is this really roughly the same as power series, which is really roughly the same as Taylor series. So if you can make a function holomorphic, you can basically compute its Taylor series, which you can get by just doing the kth derivative. The kth term is just the kth derivative evaluated at z naught over k factorial. That's the coefficient. So this is the formula I'm going to use. So let's see, what do I really want? What I really want is I want the residue of f, so I really want c to the minus 1. Well, here's what I can do. I can multiply both sides by z minus z naught to the n, and that's going to make the resulting thing essentially holomorphic. It's going to have just a removable discontinuity. So when I do that, I get z minus z naught to the n times f of z is equal to c to the negative 1 plus c to the negative 1 plus negative n plus 1 times z minus z naught plus da 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 plus c to the minus 2 times z minus z naught to the n minus 2 plus c to the negative 1 times z minus z naught to the n minus 1, which is what I want. Right? I want this. But this is a holomorphic function. It's essentially a holomorphic function. This is a regular power series, so I can use the formula for the Taylor series expansion. So I get c to the minus 1 is equal to whatever this thing is. Let's call this g of z. This is going to equal to the n minus 1 evaluated at z naught over n minus 1 factorial, which is exactly what this says, just the n minus 1 derivative of this thing and evaluated at z naught. So, there.